Good morning.
Hello, hello. Morning, good afternoon, evening, all the people joining from all over the world.
Yes, yes. Who knows what time zone's out there? I guess they're all out there, technically.
Yeah, we are globally represented. It's good to see you again, Pete.
Yeah, good to see you. It's been a little while. Been a little while. We've been hunkered down. This is winter time. I know you're in Ottawa. I'm
Yep.
in near Seattle here, so it's kind of I don't know how dark and cold it is there, but it's pretty dark and cold here. So
That fits the description. Well, I know this is our first, at least as far as I know, Edge AI talk after, the big trade show. There more to
mhm,
come. I mean, we're still coming up on Embedded World in the spring, but you were at
mhm.
CES. I feel that it
Yeah,
was good show.
it was a great show. I think they had 148,000 people there or something. So it was one of those just everything that runs on electricity. It's crazy.
Yeah.
So certainly, I think the things that I saw were, I think, a lot of interesting sensing AI and sensing stuff. Like I mentioned, like doing like AI vision without cameras and doing AI audio without microphones, and like how do you
Hmm.
sense the
Hmm.
world by using AI to interpret signals. I thought that was pretty cool. Plus, there's like cool robots, of course.
A lot of
The
robots from what I heard.
usual, margarita making, laundry folding, baloney, but actual robots too that actually did interesting things, so
Nice.
that was pretty cool. Yeah, and everyone said like their customer conversations were like customers are more educated now about edge AI, which is good. So I think
Great.
they kind of know what they want to do, and there's a lot of people out there doing cool things to help solve those problems. So that was a good thing. And
Nice.
we're going to talk to one of those folks today. We're gonna talk to
That's
Sam.
that's what we're here for. Yeah, no,
Yeah,
I mean, it's come a long way in the last few years. I mean, since the 2020s have kicked off, maybe at a trade show like that, 1 in 10 or 1 in 6 at best was like a AI educated, AI savvy tool product team, and that ratio seems to have skyrocketed to the benefit of this group for sure.
true, true. And there's some pretty cool deployments. I think I sent a picture around of myself at the John Deere booth,
Yeah,
which was
yeah, I
huge.
saw
And
that.
they had like a giant combine. I don't know how even they got it in there. How'd they get it in there? It's like maybe they assembled it in there, but it was like a real in the wheat field thing.
Yep,
So and I'm not
embedded
really
AI
talking
at
like
its
a
best.
farmer person, but I don't know the wheat field.
I didn't get that impression. I wasn't going to
You
say
can tell
anything,
I'm
but
not really a farm person, but
hey, we all eat food. If you ate today, thank a
yeah, yeah,
farmer, as the saying
yeah.
goes.
Eat
So,
bread.
yep.
But no, it was really cool. So, and speaking of events, let me do a little PSA before we bring on Sam. So we have, well, as you mentioned, Embedded World's coming up. We'll be there. We have our own booth. We're going to be sponsoring the IoT Stars event on March 10th. Get the dates right. And then March 11th, we're actually having a media dinner party event as well out there. So if people are heading to Nuremberg, and we'll have a booth. And then I'm sure NXP will be there in force, right? With some
Yes,
giant
that,
city of NXP things
the city of
happening.
NXP. I think sometimes the successful lessons and demos from CES get repurposed and reshown or
Yeah.
re-updated for Embedded World. And I think sometimes this might be the case where some of the secret or private room demos, as we call them, from
Mm,
CES become more public in the Embedded World.
mm.
That's not always the case. I can't promise that, but
Right.
definitely check it out. Yeah.
Right. Well, Embedded World's a little more focused, even though it's another 100,000 person show. It's 100,000 embedded folks.
Yeah.
So
Exactly.
uh, it's pretty intense. But then after that, the foundation's having our US event in the spring, March 24th to the 26th, which is in San
Right.
Diego.
Right.
So that
That's great.
is what we call Edge AI San Diego 2026, and March 24th to the 26th, 3 days. We have 6 keynotes, including Durga Malati from Qualcomm. We have Doug Smalls, who's a Rear Admiral, U.S. Navy. We
Very cool.
have Stacy Schulman, who's a retail executive who's with Intel. We've got 2 professors, one from UCSD, one from UC Riverside. We've got CEO of DeepX from Korea, Lakwon Kim. I think
Great.
15 hours of workshops, hands-on workshops. We've got panels. We've got, and it's San Diego, so it's going to be beautiful. We have a great space kind of overlooking the harbor,
Hmm.
and great place. We're going to have a career edge corner where you can you can get some speed mentoring. So we'll have folks there to do some speed mentoring and job postings and career roundtables. And I'm probably leaving out some things, but if you go to San Diego 2026 AJIFoundation.org, you should be there if you have any interest in this space. And I guess if you're watching this live stream, probably have some interest in the space. I know it's a schlep if you're like on the other side of the planet. I get it, but if you're able to make it, it's going to be a lot of fun and really valuable. So looking
Hey,
forward to
it's
that.
not the Hyatt Regency Burlingame. For the
It is not. Yeah,
maybe we can bring Sam on now. I know we've got 54
yeah.
minutes
Let's bring
left.
him on.
Let's jump into it. But yeah, Edge AI San Diego. Hey Sam.
Awesome. Here
Good
he
morning,
is.
Davis, Pete.
Good to
Good
see you.
morning. Good to see you.
Yeah.
So let's start by you tell us where you're dialing in from.
Well, I'm actually in the Midwest. I'm actually in Nebraska today. Typically, though, I'm in Austin, Texas. Instead, some
Awesome.
family
Yes.
stuff I
Maybe
had to
that's
deal
a
with
tie
this week.
into my comment about the John Deere combine. They probably use a lot
That's
of them
right.
out
They
there.
have a lot of that stuff here.
It's going down the road.
Yeah.
Cool. So Sam, give us a little intro. What's your role at MemryX, or how long you been there?
Yeah.
What's your
So I've
what's the
been
org?
at MemryX about a year and a half now. I'm the director of marketing, responsible for our various products. We sell both chips as well as various module form factors. I've been involved in this AI acceleration space for quite a while, actually. Back when I was at NXP some years ago, we were working with,
No way.
IDMXs and Layerscape devices being applied into AI and looking at various architectural approaches. And I've just found that it's a really fascinating field. The way I talk about it is that I think that we've, in the last decade, we've learned a new way to write software through these machine learning techniques. And that new way to write software requires new computational structures, to be efficient.
Nicely said. Yeah, nicely said.
Yeah.
Good point. Good point.
So
Hey, I just want to let folks know that this is a live stream so that you can put your questions up here and they will be aggregated and proposed to our speaker. So feel free to shout out. I see some folks coming in here, Marcelo, Leonard, other folks from Chile and California and stuff. But just let people know this is a live stream, so you can type away.
Okay.
There'll be plenty of time.
Yeah.
Cool. So what do you want to talk about today, Sam? What's on
I want to tell everybody about our product line. Essentially, the both the hardware attributes, architectural attributes, which are somewhat unique, as well as the software. What kind of problems we're well suited for solving? Why it makes a lot of sense to consider this approach to AI acceleration, which is really well suited for. There are applications where you need on the edge, right? You need a low power, small form factor device, but you need a high level of performance that you might have initially developed on a GPU. But now you're just running the inference portion. You don't really need the cost and participation of the GPU. And with a terrific solution in those cases and in others as well.
Yeah. Actually, one of the things I noticed about, because I talked to Keith, your CEO, probably a month or two ago, one of the cool things, and you'll get into it, is there's this trend now to really think about the interplay between memory and processing. And that tends to be the bottleneck these days in terms of efficiency. So the big news, I guess in December now, is like Grok, the Grok NVIDIA deal, where NVIDIA shelled out some big shekels for Grok. And the thing behind Grok was it was not a GPU; it was a much more focused processing unit for language models. But the secret sauce was also like how well integrated it was into the memory subsystem.
Yeah.
And so you get this high performance. So that's a trend right now, is like the cutting edge stuff is really thinking about the memory subsystem and the processing sort of as one holistic unit. So I don't want to spoil you a thunder here, but
Yeah, no, a lot of architectural parallels between what the folks at Grok did and what our folks at MemryX have done.
Nice. I think like many of the audience, I'll be eagerly in listen mode a bit too. Please, as you guys, go through the material, add questions, and Sam, Pete and I will be here to kind of augment that and make it conversational as best we can for today. But I know we've got a lot of great material. As Pete was alluding to, this non-von Neumann, aspiration and really going a bit farther term, beyond the economics, beyond the politics. I think you guys are right in the crucible of that at MemryX, and it's an exciting time for sure.
Yeah, very cool. So I brought your slides up. Davis and I, like I said, we'll pop in once we get some questions under our belt here, but we'll give you some runway to kind of get started. So we'll fade into the background and give you the floor, sir.
Okay, thank you. Thank you.
Take it away, Sam.
So I appreciate the opportunity to talk with everybody today, and I want to share what we're doing at MemryX and why it's a pretty compelling approach, a very compelling approach to edge AI, and the fact that we're leveraging it as initially as an accelerator that can be deployed with virtually any compute system. Makes it very easy to add this capability into existing products. So we sell this AI acceleration. We are selling both chips as well as modules. This is the M2 form factor. We've got some other modules in development as well, various form factors. But the concept is that it's a very scalable architecture. In fact, this image, you see the four MemryX devices on a stick, and those are able to be daisy chained to create higher levels of both capacity and performance. And even more important than the technology, the nuts and bolts of the technology, is the real focus on simplicity in deploying and supporting the product. So the ability to kind of take a model as it exists and to easily compile it and port it onto our architecture is a hallmark that I'll go into more detail, but it's really important. There's a lot of companies are working to solve this problem of how do I map these complex algorithms onto hardware. We did it in a co-design method, whereas we were developing the hardware and software together, and that's resulted in something that we think is really quite elegant as a solution. Fitting the edge AI foundation, we are very much focused on what we call edge segments, the industrial segment, edge servers, things on the factory floor, video management systems at the enterprise level, as well as robotics, IoT, ag tech, those John Deere tractors. We'd love to solve their problems as well, and just overall security. But it really is about being able to deploy a high level of AI processing at the end node or the edge node, where it can be, you'll have low latency, and you'll be able to have the security, the low latency, and solve the problem there without any reliance on cloud data centers to support any of this processing. When we think about what we've done, and I mentioned this at the very beginning, we've really learned a new way to write software, and this approach where we train algorithms, it's very powerful, but it is extremely computationally expensive. And it's also massively parallel, which is good because you can develop structures to process it well. By doing that, you have a lot of parallelism that is both temporal parallelism. In other words, data gets passed from layer to layer, and you can kind of pipeline things and process things in a pipeline fashion like we've been used to for years. But there's also a lot of spatial parallelism, where you're able to take operations and perform them across parallelized hardware to get high levels of throughput and performance. And of course, architecturally, well, these algorithms, they never have a constant level of both spatial or temporal parallelism. So you have to look at architectures that allow some flexibility in how the processing elements are deployed to allow this parallelism, however it presents itself, to be maximally utilized. So I know within a lot of existing SoCs, MPUs, MCUs, larger devices, there's a lot of effort and focus around how do you take an algorithm, a model, an AI model, and how do you map that to CPU cores, GPU cores, NPU accelerators, DSPs, and other processing elements that'll all have their own instruction set architectures, their own APIs for calling them. But there's a lot of complexity in trying to take these models and optimally map them to what are in reality hundreds of different architectures, all with their own little quirks and bottlenecks and things. So, you know, I think this is a good thing. I mean, I've watched a lot of these Edge AI Foundation talks, and I'm aware of a lot of companies working to solve this problem, and, you know, there'll be business there. But if we step back and look at what are we really trying to do, we need to recognize that this is, you know, that the future will be developing architectures that are AI first, right? That are designed to process these enormous AI models that have got, you know, millions and billions and trillions of weights, and that the data flows through in this as tokens, and they get processed. But that's where the silicon investment is now. And the CPUs and these other things that we've used, they'll still be there. They're really like a control plane to manage the things that they've always done, manage file IO, manage UIs and things like that. But the bulk of the processing is going to be around this next generation of work. And for a lot of the workloads, that's going to be inference acceleration. And that's really the focus of MemryX. And given the name of the company, we're really about trying to make that memory, solve both the processing and the memory problem together, accelerating it in memory. So now, as I mentioned, we really are seeking to make it simple. I'll step through some of our software tool chain and show you kind of what's available now. It's also, I will say, very open. Like all of our tools are already available online, free download, tons of examples on GitHub and on our site. But we want to make this simple and easy to take these models that have been developed or are being developed and be able to run them on our architecture. So the architecture, and I will let me go back to this. What we saw as we came into this market, and there were already a few AI accelerators in the market space before MemryX came to market. We've been in production since the middle of 2024. But what we saw was that there were lots of things like, people doing quantization, people doing pruning, people trying to change the models and try to fit them within the hardware, changing operators just to make it work on the hardware. And this kind of work could take months, and you're always trading off accuracy for if not performance, actually just being able to make a model fit or work. So the approach we've taken is to develop a unique at-memory data flow architecture. It doesn't require any model changes. So, I mean, obviously we're working off of kind of quantized int8 data, as everybody does. But things like that have traditionally been used, like, oh, I got to prune this and I got to do some compression here and there. I need to do quantization or retraining, or, I need pilot images to do that. All of that stuff goes away with the approach that we've taken. So it really does simplify. You train a model in your training infrastructure, you port it through our tool chain, and you get much higher levels of performance at much lower power and comparable accuracy. And one of the other things we've done is we have hundreds of models directly supported. I'll show you, kind of a list of a lot of what's available now, because what we did was we wrote scripts to go and, scour the internet for models and pull them in and try to compile them. And as we tried to compile them, we'd find, oh, we need to add this feature, this capability. We need to be able to handle this corner case. And we put that into our tool chain. So, generally things get directly supported. And then we've added some additional features and capabilities to make it much easier to, support out there, new features that come along. We can easily add capabilities to support that with our tools. So what used to take kind of months, that's like days or hours now. In fact, very easy to use the tool chain. We sit as an accelerator to an application processor. We can be connected via USB or PCI Express. The memory for the weights and the feature maps is fully contained within our devices, so there's no external DRAM that's required. So we're not, there aren't extra DRAM devices on our module, and there's no need to use DRAM bandwidth from the application processor to support the actual processing of models. So essentially you load the model gets loaded, you would stream queries through the model, and then the results get passed to the application processors. Generally, the application processor is going to interface to cameras, to microphones, displays, and other things, and run traditional application software. And this computational load of the AI model itself is completely offloaded, along with the memory bandwidth requirements, onto our device. I'll go through one other thing about the architecture, and then if there are any questions, I can pause there. So this architecture uses spatially multiplexed compute units. We've got MCE is the MemryX compute element. There are these kind of producer-consumer pairs that allow the scalability, and the memory actually sits between those pairs, so that you will configure a set of MCEs that will perform a certain task. As they perform that task and generate output data, that output data goes into a kind of a FIFO-based memory structure between the devices, and then gets processed by the next set of MCE devices. So you essentially are able to map a computer model to some set of these compute elements. And then these devices can be then connected to one another to expand the capacity and capabilities of the hardware to support even larger models or multiple parallel models or other things like that. So it's a very scalable design that allows us to essentially use the same tool chain and the same computational concept for very small problems as well as very large problems. The other things we've done is that we use our activations are all carried in a 16-bit group bfloat format. So essentially we're using the bfloat 16, and then we have a mechanism that shares the mantissa across a common layer, so that we can increase the overall performance and resolution. And it turns out this actually has made it so there's no need to do quantization aware retraining of models, because we actually are able to maintain the intermediate weights or the intermediate activations at a higher resolution. We can support 4, 8, or 16-bit weights, and actually on a layer by layer basis choose what that is. And if you would like more information, The full architecture white paper is available on our website, and there's a whole tutorial on how the weight precisions work and everything else works as well on the website, with some links that are referenced here.
Awesome. Hey, Sam, we have a couple of questions piling up, so maybe we can take a pause here. Everyone can kind of sip their coffee and see what folks have to say. Had a couple of ones coming in. Well, one of them is more of a product question from Ali, just saying, is the MX4, will that be available as an M.2 module? I think you had made reference to, did these come as M.2 modules? Is that one of the form factors that you
that is the form factor that we initially offered as a, kind of off the shelf, buy it pre-built module. We haven't announced MX4 in terms of whatever form factor we're going to offer that in.
Okay.
But we are going to be looking at, okay, what's the right form factor for rapid adoption in the market.
So you don't want to break any news here on the live.
Yeah, I'm not going to break any news. I will talk about the MX4 towards the end of the presentation.
Okay.
We got the exclusive. Okay.
Yeah. There you go. Another one here. Let's see. Talking about tool chains from Anthony. So does your tool chain perform its own compression or quantization, taking that burden away from developers?
Yes.
Yes, I think you addressed that, right.
It's a common practice nowadays for a silicon vendor. Yeah.
Right. Cool. Let's see. Another one.
This is interesting. I think if you're going to the question, I think you are. Yeah, Pete. Yeah, this is an interesting one. Yeah.
Senwen. Thank you, Senwen, for this one. How do you ensure the models loaded into your chip can be securely protected and not extractable by an attacker?
Yeah, we actually encrypt the models. So the tool chain does encrypt the model, and it's stored, transferred to the device in an encrypted form, and then we decrypt it and deploy it within the device itself.
So you're not performing the AI computation in an encrypted form while encrypting the data. Like that's not something that's feasible or expected. Right. You're encrypting and then decrypting. I think you mentioned. Okay. Yeah. Okay. Yeah. Still, there's the weights and the graph. Sorry, this is an interesting point. Are you computing all of the above, or just the weights, or as one entity?
So the what we call the DFP, the data flow program, is encrypted. So part of the tool chain encrypts that. So you couldn't break that up and try to deconstruct,
reverse engineer or something. Okay, very cool.
Right.
Very interesting. Cool. Okay, we got a few more here since we're on a roll here. From Francesco. Let's see. Topology. What topology of MCEs do you use in the module? Meaning, how are they interconnected, and what's the typical data flow?
Yeah, so the MCEs are structured as a there's a couple of different kinds. There are some that are more, they're essentially two different kinds. One that's more Mac oriented, and one that's more operation oriented. And the actual population of these MCEs is something that there's more details in the architecture white paper of how that works.
Okay.
But the main thing is they are interconnected via like a FIFO pool of memory. So as you produce a result, it goes into the pool, then it gets consumed by the next layer at the next clock cycle with some, I don't want to use the word slop, but some there's some ability to kind of match the producer consumer levels within the architecture.
Got it. Okay. Let's do a couple of more cues and then get back to the show here. Let's see.
Yeah.
Can you train the model specifically for data flow operators that you use in your inference architecture?
That's I guess a good question. We do have, when we say data flow operators, the fact that it's a data flow system really doesn't, it doesn't reflect on the training. However, so a lot of times, the operators, like, the multiply, accumulate, those type of operations are fairly standard, common, and everything supports those. We do use, for the nonlinear operators, We do have, we'll use the lookup tables. So we have a pretty broad capability to support a wide range of nonlinear operators. That's one of the things that oftentimes gets changed when between training and these changes that I mentioned were made to run on a device. Maybe it doesn't have the right kind of nonlinear operator, and so you use something that's similar. We've tried to be very flexible in supporting all of those through through a set of lookup tables for those operations.
Let's pull up one more, Davis. Or did you have a comment, Davis? Or?
No, I'm just listening intently. It's really good dialogue.
So this has
availability. Sorry. No, go ahead. No, this is the question.
Okay, so how many of these MX3s can work together? I think the question from Ali.
The current limit for the MX3 is it's 16 in a common thread, so like connected end to end. Now, you can obviously create kind of parallel threads and lay work out in different approaches. But what we run into is ultimately it's the amount of bandwidth required if you went to even larger systems, the host interface bandwidth would become a limiter, and that's something that we're looking to address in MX4.
I see. Cool. All right. Well, why don't we get back to I think you're going to talk about the MX4 next and some things. So we will exit stage right and give you the floor.
Okay. Well, we'll talk about performance next. So, generally, obviously we still run into how many tops is it or this or that. If we look at a base level, the four on our module, the 4 MX3 devices running at 1 gigahertz would be a 24 tops machine. However, what we find is that we consistently outperform competitors who have much higher tops claims. So, there's this efficiency that comes from this dataflow architecture that provides a very high level of performance with respect to the number of tops that we might otherwise claim. So, when we compare to, the various MPUs up to 3x versus the integrated MPU, like these MPUs on various x86 processors or other SoC devices, and versus the larger GPUs like the NVIDIA 4060, we're pretty consistently can provide double the performance of that using 1/10 the power. So I'll have some more details here. This actually is a chart. Now, this is very much YOLO focused, right? The YOLO bench is a set of variations of various YOLO models like YOLO 6, 7, 8, 9, various YOLO models at various small, medium, large, and resolutions. And these were compiled and run on both the NVIDIA, in this case, a couple of different GPUs, as well as their Jetson Orin AGX high-end SoC. And what you can see in this is a scatter chart that shows that the overall MemryX device offers kind of 2.5 to close to 6x better performance for running these models when compared to the NVIDIA devices, and does so at obviously lower power and lower costs. So, the level of performance we're bringing it's not a few frames per second, it's hundreds, if not a few thousand frames per second. It's high-end GPU level performance in a very small form factor. And we do support the various both Intel and ARM architectures. Those are available for download now. The drivers and the support available on the website RISC-V is also supported, although it's not available, not on the website. But if you've got an application where you really want to use RISC-V, talk to us. It's easy to make that available and help build that software. We can run in both Linux and Windows environments. And we typically, our compiler tool chain will directly consume models that are expressed in Onyx, TensorFlow, Keras, TensorFlow Lite. PyTorch is, the best thing that works right now is just to take that through the Onyx flow, and we'll take that Onyx model and support it. Okay. Let me get a little quicker here, but we're, as I mentioned several times, we have a broad set of online documents and tools. No NDAs required. There's no cost to go off and look at this stuff. You can download, you can actually build and benchmark models without having actual hardware. And, the tool chain's available for easy download from developer.memryx.com. We have a lot of example models to showcase there as well. So we get, one of the things that we get the best response from customers is the ease of use of our tool chain. So they've worked with various sets of, competitors or tried to build a system on whatever architecture. And when they come use our tools, they say, wow, that is so much easier. The way you guys have structured it, the software provided, the examples, tutorials, everything is just way easier to use. So as I mentioned, if you go to github.com/MemryX, there's a subcategory in there of MemryX examples. There's, 30 plus different examples of various kinds of models, all of the source code, both the, what runs on our device as well as what runs on the host processor. All of that's available for easy adoption and pickup and use. And there are also a set of tutorials that go from, how do you install all the software and drivers? How do you do basic inferencing? How do you do real-time inferencing? How do you do model cropping? So oftentimes, as I'm sure you guys are aware, not all of the operators, especially, some of the pre and post processing, will run on the device, and we have some automated tools to do the cropping of those and to provide the code that you use to hand the model or hand the data back to the host processor to kind of finalize the work. There are also examples for supporting both multi-stream and multi-model applications and multi-DFP applications. What this means is essentially being able to run, for example, 10 cameras through a certain model, or 10 camera streams through a model, or running, let's say, 10 different models at the same time, multi-models, and being able to kind of run through one model, get a result, make a decision, run through a different model based on what you want to accomplish. Being able to support multiple DFPs, being able to rapidly swap those DFPs, our dataflow programs, which is what we call a program that runs on the MemryX device. And then there are some tools to support, being able to do all of those easily, being able to support running within a Docker container on a hardware platform that's also already supported. A lot of these things are kind of the next level of capabilities that you'll find with these AI accelerators. So the kind of first generation is, hey, can I make a model run? Hey, look, I can demonstrate that I can run a model. And then you start getting into, well, actually, I want to be able to quickly switch between models, and I want to be able to run, I've got kind of multiple applications that want to share that model, and I've got, multiple destinations that I want to deal with the output of that model. So that next level of processing is already exists in the MemryX toolchain, and some of these tutorials kind of show how to get there, as well as calculating accuracy, tuning the the power. We can actually, if your performance requirements are lower, you can actually set and say, hey, I only need to run 30 frames a second, lower the power to support that. Or if you really want to get the most performance out of it, there are ways to kind of tune that up and get the most performance and adjust the devices to lower the power at the highest level of performance. So lots of tutorials and examples available. I think I talked enough about this. This is, I think the next slide is to go look at the site. So I'm going to try to exit out of this quickly and then share
the screen. Uh-oh. I think we lost Sam for a second there. All right. Well, I will hang here until he gets back, but that's no problem. I think he might have closed the browser. This is called live streaming, so that's what we're doing here. By the way, so here's some, while we're doing stuff, I'll show you this Edge AI San Diego QR code. So if you wanted to register for Edge AI San Diego 2026, March 24th to the 26th, I guess this is a little commercial break. You can scan that code up there, and that will get you to the registration website, san diego 2026.edgeaifoundation.org. And here comes Sam. He's back.
Sorry about that. Push the wrong
I thought
button.
maybe you hit the close browser button or something.
Yeah. Let's see.
No
here.
sweat. I just did a little commercial break. So
okay, good. I appreciate
showing
that.
my QR code up here. Okay, so you got your screen. Let's bring it back up.
Yeah.
Cool. All right, I will give you the floor, sir.
Okay, thank you. So our developer hub has a set of getting started guides on, running your first model, looking at the models, looking at the tutorials. There's a broad set of documentation, including specs, API docs, architecture overviews, and more information. The Model Explorer shows a broad set, although not everything that we've built, but a broad set of models that have already been built and demonstrated. This diagram kind of represents the size of the dot, is kind of how big the model is. And then you've got input resolution and frames per second across this axis. So there's a kind of a way to kind of look at things in that way. But there's also a set of, classification, segmentation, gesture recognition, emotion depth, emotion detection. So if I go to object detection, you'll see the object detection models starting with CenterNet, working through various person detectors, SSDs, YOLOs, YOLOs up through YOLO 11 that are now supported on the platform, and as well as like YOLO X is also supported, available. You'll see the resolution, the number of parameters, the format of the model, the frames per second. These are at a couple of different clock speeds that are available, and then links to the original source code, as well as a link to a precompiled DFP if you want to use that. So you can either go back to the original source code, edit it, do whatever, retrain, or you can take a pre-built DFP. So hundreds of various models for various applications, including ADAS driver monitoring, hand, palm detection, recognition, those kinds of things, even some speech models, all those great examples available. These are the tools for downloads, a compiler, the simulator, a benchmark tool, and an inspection tool to kind of allow you to kind of look at things. The runtime libraries, that's those what were available to run on the system. API documentation that list all of the the APIs for the accelerator. Python and C++ are the two languages that we directly support. Broad set of tutorials, as I mentioned, and the architecture overview if you want to dive deep into understanding the details of the hardware architecture. That's all here as well. So good broad set of capabilities. And the last thing I wanted to do is kind of show you what we're thinking about next with our MX4 device.
Yeah, Sam, I was just saying the QR code here is the developer.memryx.com website. So if people want to zap that, they can go directly to the website and
correct.
Look at all the goodies.
Yep. Look at all the goodies.
All right.
And like I said, everything is just available.
Awesome. All right. Let's talk about
Okay.
MX4.
Let's see. So in the MX3, the focus is on, the SRAM and the computational units share the common silicon, and that has worked very well, but it's really best suited for these computer vision models where, frankly, even though it's computer vision, the SRAM requirements are not as large as what are, these next generation generative models and LLMs and things require. So in order to support those optimally, there's a need to rethink how we support the memory. And so what we're working with is a partner company is developing the ability to stack the memory using hybrid bonding, to stack that on top of the computational elements. And that will allow us to support much higher memory capacity, but to do so in a way that allows the system to still retain the attributes of the smaller size, the architectural integrity that we have will be maintained as we're able to increase the amount of memory that is directly accessible by the devices. So this is the MX4 concept. We made an architectural announcement about that. We're in development now with this and are planning to have samples available next year for MX4. All right, that's what I had prepared to share with the Edge AI Foundation audience today. I'm happy to take more questions at this point.
Awesome.
Nice.
I was going to ask. Go ahead,
Steve.
You go.
Okay. I appreciate it. You did a nice job with the commercial break, by the way. So I'll also let you. Okay. Sam, great talk. Thank you for giving us this kind of preview into the future, but also what exists today. One question that was on my mind as you showed the examples page, I think maybe a few minutes ago, is this a good representation of the commercial or possible commercial deployments? I know you mentioned there's a big shift from the CNNs to generative models, which of course is probably a little bit familiar to this audience. Can you just talk about how these examples, this enablement has maybe built or been defined by or shaped by commercial deployments, and are we kind of anything surprising you'd want to share, anything that you can speak to in terms of how this maps to some of the real world success you guys have had with MemryX?
Yeah, so the commercial deployments that we are engaged with are heavily invested in industrial PC form factors.
Okay.
And, essentially systems that have been built around multi-camera computer vision applications where there is a need for a high level of processing and performance. We're not a great doorbell camera solution.
Sure.
We're a really good enterprise, where you're essentially pulling in a lot of information and being able to process that at a high throughput.
Gotcha.
The transition, I don't have a good feel yet for how much like speech models or language models would be at the edge. I mean, the reality is that the bandwidth, although the memory requirements are lower for video for like YOLO models, the actual weight memory requirements are lower. The data bandwidth requirements are much higher.
Yes.
So the
what about multimodality? No, you make a good point. It's nice to get a sense of where you guys have gotten that real world deployment. But what about multimodality in the sense of radar, lidar, other perception means? You are in these rugged, noisy environments. So of course, multi-camera is a start. But do you see a need for sensor fusion or at least multimodality at the edge?
Yeah. So multimodality is not I mean, for us, it's just data, right? What the form of the sensor comes from. I mean, that's the training, that's the data. For us, it's really about data and can you support the precision needed, either the size of the model or the precision of the data types. And we think we've got enough flexibility to support those things with no issue. I mean, whether it's a 3 colors plus depth, or whether there's some radar thing, whatever, that really is not something that our architecture needs to be aware of. It's just processing the data and finding the associations that we're trained to find.
Cool. Gotcha.
Yeah.
We had a couple of questions.
We got to catch up and maybe in Austin sometime. I know you're out of the town right now, but we do have obviously some offices there from time to time. But Sam, it was great to pick your brain a little bit. There's some more questions flowing in here now, which I think is what Pete.
Yes. Here's more of a general question around power consumption figures. I don't know if you had mentioned some examples.
Yeah. So it all depends on the utilization of the device. So for that memory, the stick, the MemryX M2s, or the 4 devices on that. Each of those devices has a kind of a typical 1 watt power dissipation, 1.5. I would say more likely 1.5, and then a maximum power dissipation of about 3 watts. So the whole, at a peak, we're at 12 watts, which is the limit of the M2 form factor.
Right. Okay, cool. Let's see a couple other
ones. It's very dependent on how much work you're doing because of the data flow. Like if you're not flowing through it, you're not using any power. So
cool. Question from Anthony: how many MX3 chips will be available in the MX4? I'm trying to compare scale if it's simple additions, like how does it performance-wise? I think asking
the
MX3
relative
versus
performance or relative.
No announcements there. I'm sorry.
No announcement. But it's
okay. We'll have to do another talk. Yeah.
MX4 is more than MX3. I think that's safe to say.
Well, it's. I mean, it won't. The limits are more likely the physical limits of the form factor, right? If it's an M2 device.
Right. Yeah. The M2 connector has some physical limitations, I guess. So.
Yeah.
Here's a question about kind of workloads and neural networks. And actually, Sam has a follow-on comment on this. Are certain ops in a neural network parallelizable from a computational perspective?
Well, yes.
Yes.
I guess it's how you. I guess to his follow-up question. I think the question was context for above is the mapping is more of the uniqueness. So you guys has found some, like you would, let's say for commodity hardware, you'd find some intrinsics about the instructions or the data mapping, like a commodity GPU or CPU, and intelligently, if you want more performance, map those ops to the hardware intrinsics. You guys have gone out of the way to pave your own pathway in this sense, and I guess that's what Sam's really asking is how do you map the neural networks in your TensorFlow, PyTorch, ONNX, whatever, to your parallelizable, more efficient compute platform. Right. Hopefully, I'm getting that right, Sam.
Yeah. Well, I think that the main thing is that we spend a lot of time looking at what are the most common operations, right, and really looked at lots of data about what are these the most important models, most common operations, what do we need to support. And gets to be a long tail of do I really need to do that because there's only one model that uses it. Does that matter? But we do, I mean, we're not as general purpose as as any, as a general purpose CPU.
Right.
But for this class of application, we're confident we've done a really good job of defining an architecture that's able to both take advantage of the parallelism in the data, but also has a broad enough set of operators that we can keep the core of the processing within our device. One of the things that would kill performance is if we kept having to go back and forth to the host. Right. We want to be able to, have the host kind of get things set up, hand stuff to us. We process it all the way through and we give a result back. If we have to kind of move data in the middle of a compute graph back to the host, that is
minimize memory transactions. Yeah, for sure.
Right.
With that, you mentioned that ease of use. Sorry, Pete. Yeah, that ease of use of that platform, that software is totally another value, a vector of value. Let's say. So, like you said, that efficient mapping, that hardcore great efficiency that you need for the edge, plus an ease of use software pipeline is the icing on the cake, really, which I know you mentioned in your presentation.
Yeah.
Yes. By the way, I noticed, maybe you can speak to the fact, I think you guys are hiring right now. So a lot of times we have folks in this live stream that are very talented professionals and talented students. So I see that you have a few jobs open. And in fact, I think Keith mentioned you now have a development center in Riyadh in Saudi Arabia as well as Michigan.
True. Yeah. I didn't mention that, but yes, we've set up a site in the last, 6 months in Riyadh, and got a lot of great stuff going on there. Lots of opportunity.
So you're hiring, I saw on your website, you're hiring for engineers in Taipei, in Riyadh, and in Ann Arbor.
Yeah.
So I would encourage folks that are interested.
The main engineering sites of the company.
And, get into it. Lots of geographic opportunity there with MemryX careers. So that's good. And you can say, hey, I watched this live stream with Sam. I know all about MemryX. So
you already broke the ice. Exactly.
Broke the ice. You get your foot in the door.
Yeah. Feel free to reach out if you want more, kind of more information. And I mentioned the developer.memryx.com, a wealth of information there. We also.
Right. Nice. And by the way, speaking of careers and education, so there's a question here earlier on from Salma about beginner friendly, easy to grasp. We always get questions about how people get into this space. We have actually published what we call Edge AI Fundamentals, which is an online, about 90 minutes of material to sort of get people sort of literate with Edge AI. So I put the QR code up there. If people go to cert.edgeaifoundation.org, they can sign up for the private beta. We're actually about to go public on it, but it's currently free, and you can sort of get educated again in preparation for your interview at MemryX. You can kind of learn all sorts of terms and terminologies and walk in there as a literate engineer. Nice. So I encourage people to click on that, sign up for the private beta, give us your feedback. We're going to be launching about half a dozen modules of different topics this year, but we started with what we call fundamentals. So it's good for everyone to sort of get a good baseline of literacy in Edge AI and then dig into it. So places like MemryX, I mean, the developer tools you have, the site that you have, is fantastic. So it's like, this is one of the cool things is seeing all the innovation in this kind of area of efficiency, which really is the frontier for AI, right? As efficiency is like, how do we do this faster, better, cheaper, more impactful?
We're just at the beginning of like a 40-year journey to make this stuff even better.
It's the floor, not the ceiling is the term I think I've heard thrown around, and I think it's very, very fitting.
Yeah. And just to not be too commercial, if anybody on the cast wants to, buy a device, they're available on Amazon for $149. So
cool.
Dev kits. Always love the dev kits.
Yeah.
Very good. Well, Sam, thank you so much. Davis, good to see you again. Stay warm,
likewise.
Both of you. And we'll see you in real life at some point.
Yeah.
Yes. Sounds good.
All right.
Thank you, everyone.
Thank you, everybody. Thank you.
Bye.